Welcome back to the show. Today, we're diving into a fascinating topic that's really shaping the future of technology, the semantics in stream processing and how data systems are evolving. If you've ever been curious about how we can make applications more reliable, scalable, and maintainable, you're definitely in the right place. We'll explore some key concepts like fault tolerance, data integration, and the delicate balance between distributed transactions and log-based systems. So, grab your headphones and let's jump right in. Let's start with stream processing. Unlike batch processing, which deals with data in chunks, stream processing is all about continuous operation, producing outputs in real time. This real-time aspect means that when a task fails, we can't just throw everything away and start over. Instead, we need a more nuanced recovery mechanism. Techniques like microbatching, checkpointing, and idempotent writes become crucial in this context. They help us recover from failures while preserving the valuable data that's already been processed. Now let's shift gears a bit and consider a philosophical perspective from St. Thomas Aquinas. He once said that if a captain's highest aim was to preserve his ship, he'd keep it in port forever. This idea resonates deeply with application design. If we focus solely on maintaining the status quo, we might miss out on opportunities for innovation. Today, we'll explore how we can design applications that not only fulfill their current purposes, but also evolve to meet future needs. As we delve deeper, we'll notice some recurring themes: reliability, scalability, and maintainability. These aren't just industry buzzwords. They form the bedrock of solid application design. We've touched on various fault tolerance algorithms that enhance reliability, partitioning strategies that boost scalability, and abstraction mechanisms that improve maintainability. The ultimate goal here is to create applications that are functional today and ready to tackle future challenges. One of the most significant hurdles in application design is the complexity of data systems. When it comes to storing data and retrieving it later, there's no one-size-fits-all solution. Different storage engines, like log-structured storage, B-trees, and column-oriented storage, each come with their own strengths and weaknesses. The key takeaway is that the choice of software tools should be tailored to the specific circumstances of your project. As applications grow, so does the need for effective data integration. Often, data is represented in various ways across different systems. For example, you might need a database for record keeping and a search index for handling queries. This duality can complicate matters. You may find yourself needing to synchronize data across multiple systems, which raises important questions about consistency and accuracy. Here's where it gets interesting. Engineers often make broad assumptions about what users need based on their own experiences. However, the reality is that data requirements can vary widely. What seems unnecessary to one person might be critical for another. To address these diverse needs effectively, it's essential to zoom out and consider the broader data flows within an organization. To manage different access patterns effectively, clarity about data inputs and outputs is vital. You need to understand where data is initially written and how various representations are derived. For instance, if data is first written to a system of record and then applied to a search index, maintaining that order is crucial for ensuring consistency. This approach, known as change data capture, helps keep systems aligned and reliable. Now let's talk about distributed transactions. Their purpose is to ensure that changes are applied exactly once, using locks to manage writes. While this method has its advantages, it also comes with limitations, particularly regarding performance and fault tolerance. On the flip side, log-based systems present a compelling alternative by leveraging deterministic retry and idempotence, which can simplify recovery from faults. Many experts believe that log-based derived data systems represent the future of data integration. They offer flexibility, but often at the cost of eventual consistency. It's essential to find a balance between the benefits of asynchronous updates and the need for stronger consistency guarantees. As we scale systems, we face challenges in maintaining a totally ordered log. For example, if events have to pass through a single leader node, it can create bottlenecks. Introducing partitioning or geographically distributed servers can make the order of events ambiguous. This is a significant consideration, especially for applications deployed as microservices, where independent services might generate events in different sequences. This brings us to consensus algorithms, which aim to establish a total order of events. Most traditional algorithms are designed for scenarios where a single node can handle the entire event stream. However, as workloads increase, we need new consensus algorithms that can scale and function effectively across distributed environments. This remains an open research question, and finding a solution could revolutionize how we manage data. So, what's the takeaway from today's discussion? As we look towards the future of data systems, it's clear that we need to embrace complexity while striving for simplicity in design. By understanding the nuances of stream processing, data integration, and the challenges of distributed systems, we can create applications that are not only robust and scalable, but also ultimately beneficial to humanity. Thank you for tuning in today, and we hope this conversation sparks new ideas and discussions in your own work. Until next time, keep pushing the boundaries of technology.